Hello, in this video, we are going to talk about some theorems that tell us essentially how good the approximations are. Because in the last video and the video before, we saw that we can approximate a function using a Taylor polynomial. And then once we use that Taylor polynomial to find an approximation, we want to know how good is that approximation. So to first define this, we have the remainder in a Taylor polynomial. So we know that a function is approximately the nth Taylor polynomial, as that is what we're using to approximate. Using the idea of series and remainders in series, it's that there is this function that is equal to the nth Taylor polynomial plus some remainder function. Meaning, this remainder function, by just rewriting things, is our function f of x minus the nth Taylor polynomial. So there is a remainder. It is called, well, we call it the remainder. It's telling us the error between the function and the Taylor polynomial. So we're trying to see how small can we get that to be? How many terms may we need in our nth Taylor polynomial to make the error small enough? And that is where Taylor's theorem, or the remainder theorem, comes in. So it says, let f have continuous derivatives up to the n+1 derivative on an open interval. So basically, we can keep taking derivatives for as long as we need for this theorem to work on some interval. For all x in the interval, the function is equal to the nth Taylor polynomial plus the remainder. Remainder can actually be found, and it can be found using the mean value theorem, or at least proved using the mean value theorem, that this remainder is actually the n+1 derivative at some point c over n+1 factorial x minus a to the n+1. What this looks like is the coefficient. The n+1 coefficient would be f to the n+1 at a over n+1 factorial x minus a to the n+1. That would be the coefficient. The remainder looks very similar. The difference is this c. And what that c is saying is we're not doing the n+1 derivative at a, we're doing the n+1 derivative at some point between x and a. We don't know what that point is. That point could be x, it could be a. It is somewhere between x and a. We just don't really know what that is. So the remainder can actually be found if we knew that c value to be the n+1 derivative at c over n+1 factorial x minus a to the n+1 for some point c between x and a. Because we don't really know what this c actually is, the best we can do is estimate the remainder. So the estimate of the remainder is the absolute value of the remainder is going to be less than or equal to m times the absolute value of x minus a to the n+1 all over n+1 factorial. how we will find m is the largest absolute value of the derivative. So we will, of the n plus 1 derivative. So we will find that n plus 1 derivative and say that where that largest value takes place, most of the time we'll have an increasing or decreasing function, so we can find that largest value easily. But we'll find the largest value of the n plus 1 derivative, and that we will take to be m, because we know there's some value that gives us this remainder. If we find the largest that value could possibly be, we can estimate the remainder. We will take a look at about 3 examples of this idea in the next videos.